Hello, so in this video we are going to start looking a little bit more at algebra and then we're going to move on to some surds and some indices later as well. So if you remember in the last video we started looking at algebra and we specifically looked at questions which involved simplifying and working with algebraic expressions. And of course we looked at the difference between algebraic expressions, equations and also identities as well. Now in this video we're going to start looking at solving some things. Now to solve something simply means find what you don't currently know, okay? So for example, if I give you 5x equals 10, you remember with algebra, one of the biggest uses of algebra at least, is actually finding unknowns, okay? So working with things that you don't currently know the value of. In this case, the thing which we don't know the value of is the x, okay? So just remember, what's going on here? We're basically saying, take some value, in this case x, then what we're doing is we're multiplying that value by 5, okay, so we multiply that value by 5, and then we end up with 10 at the end. So in other words, we're saying, what number, when I multiply it by 5, should give me 10? Well, hopefully, by just trial and error, you should be able to realise that that number should be 2, because 2 times 5 equals 10. But what I'm going to show you is the technique of playing it backwards. So it's almost like you're playing a song, but playing it backwards. Okay, so here, instead of going forwards along the chain, okay, so instead of going forwards along the chain, what I want you to do instead is to work backwards along the chain. So in other words, instead of starting at something you don't know and ending up with something you do know, I want you to go the other way. I want you to start at 10, work your way backwards, and then we get to the thing which we're after. Okay, so what is the opposite of timesing by 5? Well, quite simply, it is going to be dividing by 5. Okay, we're going to divide by 5. So in other words, what we're going to do is divide by 5 on both sides of the equation. Now you notice in this case it is an equation because there's an equals down the middle. The equals means equivalent to, it's the same. So in order to keep these two things balanced, in order to keep the two things the same, you need to divide by 5 on both sides, otherwise you change the value. So if you divide the left-hand side by 5, you'll just end up with x. If you divide the right-hand side, you end up with 2. And there's your final answer. So x equals 2. And I want you to play with this. Even though with simple equations like this, you might be able to go, all right, that answer's got to be 2, because 5 times what gives me 10? It's got to be 2. But what I want you to do is get into the habit of playing it backwards. Okay, playing this thing backwards and then doing the same thing to both sides, just like we did over here. So you realise to get rid of that times by 5, you have to divide by 5, because that will help us out when things get slightly more challenging. So as an example, let me try this on you. If I give you something like y minus 1 equals 9, what you're literally saying here is you start off with a value, you take away 1, then you end up at 9. So if you want to play your life backwards, it means you start at 9. What's the opposite of taking away 1? Well, it's got to be plusing 1, and then you'll end up with what you're after. Okay, so if you start at 9 and you add 1 to it, you'll get at 10, which means that y has got to be 10. So in other words, what I did here was I added 1 on both sides. I got rid of that take away 1 from the left-hand side. So in other words, I'm just left with y equals 10. All right? So there's two ways you can think about it. Either doing this method where you're reversing it on both sides, or you're thinking about it as a chain. Okay? All right, let's try the next one. Let's try this one here then. Let's try something like 2z plus 5 equals 15. All right, so 2z plus 5 equals 15. Let's see if we can play this backwards. So first of all, you're taking z, that's your unknown. First thing you're going to do is times by 2. Just remember your order of operations, okay? The multiplication comes before the adding, so therefore you've got to multiply by 2 first. So you multiply by 2 first, then you add the 5, okay? Then you add the 5. And then you end up at 15, okay? So if you want to play this backwards, the first thing you've got to do is take away 5 from both sides, okay? So let's take away 5 from both sides, and let's see what we get. Right, so on the left-hand side, if we have 2z plus 5, but then if we take away 5, you're just going to be given 2z. Then if you have 15 and take away 5 on the right-hand side, that's going to be 10. Then you've still got to carry on working backwards because you're not quite there yet. So therefore you've got to undo the times by 2, which means you're going to be dividing by 2 on both sides. So let's divide both sides by 2. So on the left-hand side, 2z divided by 2 is just z, and then 10 divided by 2 is 5. And that's it. So z must be 5 in this case. So again, you could have looked at this and thought, what number when I times it by 2 and then add 5 gives me 15? And you could have maybe done a bit of trial and error, but this way is going to get you out of jail free every single time. All right, let's try something a little bit more tricky then. Let's try something like this. So let's try a plus 6 equals 7a minus 12. Now something like this is, well, it's not impossible to do by trial and error. You would get there eventually, but it's much easier to do the methods which I've just shown you. So let's first of all get all of the terms on the same side. So in order to get the terms on the same side, I mean either take the a on the right hand side or get the 7a on on the left hand side. So in other words, I'm looking at the terms which have the unknowns in, and I want to bring all of those together on the same side of the equals. So what I'm actually going to do is take the a on that side. So just remember, what is the sign in front of the a? Well, the sign at the moment is a positive, right? I just haven't bothered to write it, okay? So if I want to get rid of the a from the left-hand side, what have I got to do? Well, quite simply, I've got to take away a, okay? So the opposite of adding a is taking away a from both sides. So on the left-hand side, well, if I have positive a and I take away a, haven't got any a's there, but I've still got a 6. Then the right-hand side, I've got 7a, and I'm taking away an a, which means that I'm going to be left with 6a. And of course, I've got the takeaway 12. Now, just because I think it's slightly easier to look at the unknowns on the left-hand side and a number on the right, I'm just going to switch these two sides around. Okay, so I'm just going to do a switcheroonie and put the 6a minus 12 on the left-hand side, and then just leave the 6 on the right-hand side. All right? Okay, fine. Now what I need to do is work with this. So first things first, I'm after the a. Okay, now you could think about this with my chain examples, which I've done before. Okay, so you could think about it like this. But the more practice you get, the more familiar you will get with what order to do things in. So first things first, I need to add 12 on both sides. So if I add 12 to both sides, I get rid of this plus 12 here. So I'm just left with 6a here, then 6 plus 12, that gives me my 18. All right, fine. What's left to do now? Well, I need to divide both sides by 6 in order to get rid of that 6a. So I'm just going to be left with a here and 3 here. There's my final answer. Okay, so hopefully that makes sense. All right, let's just try one more example then of this type. So let's try c times by c minus 4 is equal to c squared plus 12. All right, let's have a look at this one then. So first things first, I don't like the brackets being there, okay? So I'm going to expand these brackets out. This is what's making it different to the things which we've seen before. So if I expand the bracket out, we did this in the last lesson. We did c multiplied by the c gives me c squared, and c multiplied by negative 4 gives me negative 4c. And the right hand side hasn't changed. So all I've done there is just simply multiplied those two brackets out. All right, good. Now we need to get everything on the same side, so all of the unknowns on the same side. So you notice here, I've got c squared on this side and then loads of c's on this side. I think it makes more sense to bring this c squared here over onto the left-hand side. So in order to do that, well, at the moment, there's a positive c squared there. Okay, it's just not bothered to be written in. So it's positive c squared. So how do I get rid of that positive c squared? Well, I need to take away the c squared. And I need to do that to both sides. Okay, so in other words, on the left-hand side, I get c squared minus 4c, take away c squared, has got to be given 12 on the right-hand side. Now have a look. C squared, and I take away c squared. Collect together those like terms like we did in the last video. C squared take away c squared is just going to give me 0, okay? So therefore, I'm just going to be left with negative 4c on the left-hand side and 12 on the right. Now, if you look at this, have a look what I've got here. Don't worry about the negative for the time being, just ignore that. I've got 4 times by c. In order to get rid of that 4, I'm timesing by 4, so I need to divide by 4. So I need to divide both sides by 4. Okay, good. So if I divide the left-hand side by 4, well, I've still got the negative there, even though I haven't considered it, but it's just going to be negative c. And if I divide the right-hand side, well, 12 divided by 4, that gives me 3. Okay, but the issue is I don't want negative c. I just want the c on its own. Okay, remember this whole kind of point of solving equations like this, is you're trying to isolate the thing which you don't currently know. Okay, so in this case, I've got negative c equals 3. Okay, so in order to get this on its own, what I'm just going to do is divide both sides by negative 1. So if I divide both sides by negative 1, because you can almost think of this as negative 1 times c. Yeah, you can almost think about this as negative 1 times c. So in order to get rid of that negative 1, I can divide by negative 1. So if I divide by negative 1, well, negative c divided by negative 1 is just going to give me c, but 3 divided by negative 1, that gives me negative 3. So that's my final answer, okay? So hopefully that makes sense, all right? Now, let's carry on with the solving examples, okay? But let's try a slightly more tricky one with fractions. So let's give you something like this. X plus 1 over 3 plus x minus 4 over 2 gives me 5. Okay, so let's have a look at this one then, okay? So first things first, don't get freaked out by the fractions on the left-hand side. Just use your trick of simplifying it. So don't think of that this is a solving equation immediately. Just have a look at those fractions. We don't particularly like fractions to solve equations because it makes things a little bit more awkward. So the first thing you need to do is get rid of that fraction. And the way to get rid of it is to simplify it. So it's just one fraction, because one fraction is better than 2, right? So in order to simplify this fraction, we did this in the last video, you need to find a common denominator first of all. So in this case, my common denominator will be the product of these two things multiplied together. So 3 times 2, okay? So 3 times 2 gives me 6, so 6 goes in the denominator of each of these fractions. Then just think, what have I multiplied that first fraction by in order to get a 6 on the denominator? Well, I've multiplied by 2, so I need to multiply the numerator by 2 as well. So 2 times by x plus 1. Same thing, just make sure the plus is in the middle still, because I've still got a plus there, all right? Same thing with the second fraction. What have I multiplied the denominator of the second fraction by in order to get 6? Well, I've gone from 2 to 6, so therefore I've multiplied by 3. So I also need to multiply by 3 on the numerator of that second fraction as well. So I'll get 3 times by x minus 4. Okay. Now I'm still going to keep the equals 5 in there, even though I haven't really done anything there. I've just simply copied it down. Okay. So now I can simply write these two fractions as one big fraction. So it's all going to be over 6. And I'll end up with 2 times by x plus 1 plus 3 times by x minus 4. That's all going to be equal to 5, even though I'm not considering that at the moment. Now I'm just going to expand out the numerator, okay? So if I expand out the numerator, what do I get? So if I expand out the numerator, let's expand each term separately. So 2 times by x plus 1 is going to give me 2x plus 2. And then 3 multiplied by x minus 4 is going to give me 3x minus 12. And that's all still over 6. That's going to equal 5. All right, good. So carry on working with this then. So let's again just simplify that numerator just by collecting together like terms. 2x plus 3x, that gives me 5x. And 2 minus 12, that is going to give me negative 10. And that is all still over 6. Okay, good. And I've still got that equal to 5. So now I'm in a position where I've gone from two fractions being added together, and it equals a number, to suddenly just getting one fraction equals a number. That's simplified. Now I've actually got to figure out what to do with this fraction. Well, just think, okay? What does this over 6 actually mean? What does the over 6 actually mean? Well, in this case, you can just treat it as divide by 6, okay? You can think about this entire 5x minus 10 as divide by 6. So in order to get rid of divide by 6, what have I got to do? I've got to multiply by 6 on both sides. Because of course my aim is to get that x isolated. So in order to get the x isolated, I first of all need to get rid of that over 6. Okay? So if I multiply both sides by 6, on the left-hand side I get 5x minus 10. On the right-hand side, well, 5 times 6, that gives me 30. Okay? Now it's exactly the same examples as we've seen before. Okay? So I just need to add 10 to both sides to get rid of that take away 10. So on the left-hand side I get 5x. On the right-hand side I get 40. And then all I need to do is just divide by 5 on both sides, and then I get x on its own, and then 40 divided by 5, that gives me 8. So in other words, in this case, x must be equal to 8. Good, fantastic. All right then, let's see what else we can do. Let's see if there's a slightly more tricky example which we can look at. Okay, so what question are we up to? Question 7. Let's have a go at this question here then. All right, if we have 6x and we're dividing this by x minus 1, then we want to take away 5x divided by x minus 2 equals 1. All right, so let's have a look at this then. So similar kind of thing to before. Don't worry about the fact it's equal to 1. Just simply focus on simplifying these two fractions to make one big fraction. okay? So in order to get one big fraction, I've got to multiply the denominators together, okay? So in the denominator of each fraction, I should end up with the product of these two things. So in other words, x minus 1 times by x minus 2 on the denominator of each fraction, like so. And this is still equal to 1. All right, fine. Now what I'm going to do is just ask the question, same as before, what have I done to the first fraction in order to get that denominator? In other words, x minus 1 times by x minus 2. Well, I've simply multiplied by x minus 2. So in other words, I'm going to get 6x times by x minus 2 if I multiply by that on the numerator as well. Similar question with the second fraction, okay? Well, I had 5x, but what have I done to get that same denominator of x minus 1 times by x minus 2? Well, I've multiplied by x minus 1. Okay, so in other words, I've multiplied this by x minus 1 as well. Okay, now again, just keep going. I can now write this as one big fraction, can't I? Because I'm just subtracting two things, two fractions with the same denominator. So let's have a look. Well, I have 6x times by x minus 2 minus 5x times by x minus 1, all divided by x minus 1, x minus 2, and that's all equal to 1. Okay, so now I can just kind of keep going with this. So I'm just going to figure out what I get on the numerator, just if I expand this out. So let's have a look. Well, if I have 6x times by x, and then 6x times by negative 2, if I expand that first bracket out, I get 6x squared minus 12x. Now I've just got to be careful with the second one, haven't I? Because I don't just do 5x times by each of these things, because look, I've got the negative in front of the 5x. So I need to take negative 5x and multiply it by each of these things. So negative 5x times by x is going to be negative 5x squared, and negative 5x times by negative 1 is going to give me positive 5x. All right, fantastic. Okay, and everything else stays the same. So now I'm here, I guess I can just simplify these like terms on the numerator. So have a look at the numerator again. Well, I've got 6x squared take away 5x squared. That's going to give me x squared. Now I've got negative 12x plus 5x. That is going to give me negative 7x, isn't it? And then on denominator, I still keep that the same. So x minus 1 times by x minus 2. And I've still got all of this equal to 1. All right, so now I've just got my single fraction, which I'm after. So instead of having two different fractions, which look kind of quite frankly horrible, I've now got a single fraction which I can work with. Okay, so how am I actually going to work with this? Well, first of all, I'm after the x. Now, in general, I always say keep all the letters on the same side. Okay, so you can see here all the letters which I'm after, all the things I'm trying to solve for, they're all on the left-hand side. However, there is one exception to that rule, which is if you've got a fraction. If you've got a fraction, always, always, always get rid of the fraction first. Okay, so in order to get rid of the fraction, just remember this means divide by the entire denominator, divide by x minus 1, x minus 2. So I need to multiply by that denominator on both sides. So I need to multiply by x minus 1, x minus 2 on both sides. Okay? So on the left-hand side, if I multiply by that denominator, I should end up with x squared minus 7x. Okay? Because if I divide by x minus 1, x minus 2, then immediately multiply by that x minus 1, x minus 2, I'll just be left with the x squared minus 7x. Okay? On the right-hand side, I get 1 multiplied by all of this thing. So it'll just be 1 times by x minus 1, x minus 2, like so. Okay? Now, this looks a lot friendlier because look, as soon as I see a bracket, my kind of mathematical instincts are kind of perking up and I'm like, I can expand this bracket. So come on then, let's see what we get if we expand it. We did some examples of these in the last video. Okay, so if we expand it out, we get x times by everything in the second bracket. So we get x squared minus 2x. And then this negative 1 visits everything in the second bracket as well. So negative 1 times by x is negative x, and negative 1 times negative 2, that makes positive 2. So just a bit of simplification then, x squared minus 3x plus 2. I've just simply collected together these two like terms in the middle there. All right, fine. So in total, I have x squared minus 7x. So first things first, let's get all of the x's together on the same side, okay? So I'm going to take away x squared first of all from both sides, okay, because I see an x squared there, okay? So I'm going to get all those x's together. So if I take away x squared on both sides, I get x squared minus 7x take away x squared. On the right hand side, x squared take away x squared, that's gone. So I'm just left with negative 3x plus 2. Okay, I can make a little bit of simplification because look, I have an x squared and I'm taking away an x squared there. So if I collect together those like terms just as I'm going, that'll just only leave me with negative 7x. And on the right hand side, I'll still have the same. Now I want to take the other x over on the other side. So you see this negative 3x, I want to bring him over here. Well, how can I do that? I can do that by adding 3x to both sides. Okay, so if I add 3x to negative 7x, I get negative 4x. And obviously on the right hand side, I'm just left with my 2. Okay, now in the same position as before, we've dealt with negative situations before. So all I need to do is get rid of that 4 first of all. And I'm going to do that by dividing both sides by 4. Okay, so I have negative x on the left hand side. 2 divided by 4 is a half. Okay, and then finally, I just need to get rid of that negative x. Officially, what I'm doing is dividing by negative 1, but I'm happy if you want to think about this as just flipping the signs of both sides. That is also fine. Okay, so x finally will be equal to negative a half. So the thing which I started off with, all up here, all the way up here, this thing here, this really horrible looking thing, the solution to this equation, the thing which will make this thing equal 1, everything on the left hand side equal 1, is negative a half. Okay, now this is where it's really useful. You remember, as I said right at the very beginning, if you think about it intuitively, you know, when I started off with like 5x equals 10 or whatever it was, yeah, this one here, when I started off with 5x equals 10, this one was easy to find, right? X equals 2, that was easy. But now the one which I've just done, all the way down here, okay, trying to find out that x equals a half, like just by trial and error looking into that, I mean, you might get it eventually, but I would never know to guess there. Okay, so this is where actually just having a systematic approach of solving equations is really, really important. Okay, so hopefully that kind of makes sense. All right, so let's move on then to surds. This is the next kind of thing which we want to look at. Okay, now a surd is just simply a square root that doesn't result in a nice rational number. So let me show you what I mean. Okay, if I talk about squaring something, okay, so if I say to you like 1 squared, what does that equal? Well, hopefully you'll tell me that's 1. It just simply means 1 times 1, right? If I ask you, what does 2 squared equal? That means 2 times 2, so hopefully you tell me that's 4. If I tell you 3 squared, what does that equal? Hopefully you tell me that's 9. And 4 squared, that equals 16. And 5 squared, that equals 25, etc., etc., etc. Okay? So in other words, if you take a number and you square it, you can think about this as multiplying the number by itself. Now, there is actually something interesting going on here. If I look here at 1 squared, okay, why do I say 1 squared? Okay, why do I actually say 1 squared? Because if I give you something like this, like 1 and then the 4 up here, you would say this as 1 to the power of 4. But here you don't say 1 to the power of 2, you say 1 squared. Why? Why do you say 1 squared? Well, there is actually a reason. And the reason is all to do with squares. Surprise, surprise. So if I draw out a square for you, just remember that a square, I mean that's a rubbish square, let me just do a slightly better one. I mean it's not great, but it's fine. Just remember that a square, by definition, is a quadrilateral. All of the angles are right angles, okay, they're all right angles to each other. But crucially, all of the sides are the same length. Okay, so this side, this side, this side, and this side, they are all the same length. They are all equal to each other. Okay, so if I look, for example, at this one down here, so 5 squared, what has this got to do with a square? Well, the answer is that I am looking at a square of side length 5. In other words, all of these side lengths are 5. Okay, but then what is this actually doing? What is 5 squared actually doing? How do I get 25 from a square like this? Well, the answer is if I'm finding the area. Because if I want to find the area of a square, I simply multiply the height by the base. Okay, so to find the area of a square, I multiply the height by the base. In this case, the height and the base are all the same because it's a square and all the side lengths are the same. So therefore, when I say 5 squared, what I'm literally asking for there is what is the area of a square with side length, in this case 5, okay? So the reason why I say 1 squared or 2 squared or 3 squared or 4 squared or 5 squared is because on this side I'm looking at the side length of a square, okay? So in this side, this kind of column here, for example, this column here is asking me, okay, this is the side length of my square. So this one would be side length 1, and then side length 2, and side length 3, etc., etc. So on the left-hand side, I've got the side length, which means that on the right-hand side, I have the area. Okay, so on the right-hand side, I've got the area. So this question here, for example, 2 squared. I'm literally saying if I have a square with side length 2, what is the area? So the act of squaring something is literally asking, what is the area of my square? Okay, so that's how I get the right-hand side. All right, so the act of squaring, the reason why I say 1 squared or 2 squared rather than 2 to the power of 2 or 3 to the power of 2 is because I'm literally looking at a square where that is the side length. So it's 3 squared, 3 is the side length, 9 is the area. Now this is nice, okay, so this is a really nice way of going from the side length to the area. But my question is there an operation which takes me back in the other direction? In other words, I say, here's the area of my square, what's the side length? Okay, and the answer is yes. So for example, if I start with an area of 25, so on this side I've got area now, and I want to get back to the side length, is there a way of getting back the other way? And the answer is yes, absolutely. I need to take the square root. Okay, I need to take the square root. So in other words, if I say I have a square with area of 25, this is what this question is asking, what is the side length? You would tell me that is 5. The reason why you know that's 5 is because you look up here, right? And if you look up here, you realise that it's just the opposite of squaring. The way which you can think about this square root of 25 is, what number when I multiply it by itself will give me 25? And the answer is 5. Another example, okay, if I take, for example, square root of 16, you're literally asking yourself the question, what number when I multiply it by itself will give me 16? That will be 4, okay? Now, you see on the left-hand side up here, when I was going from side length to area, okay, I could basically stick any number I like over here, and it will always come out with a nice area. In other words, what I mean by nice area is it will be an integer if I stick an integer in on the left-hand side. So let's see that if the same thing is true on this side, okay? So if I say, what is the square root of 1, for example? Well, the square root of 1, what number times itself will give me 1? That's going to give me 1, okay? But then if I try to take, for example, the square root of 2, you're like, what number when I multiply it by itself is going to give me 2? And the answer is, well, I don't know. So this is where you can come over to your calculator. If you look on your calculator, there should be a square root button. It's usually kind of fairly close to where the powers and things like that are. Okay, so if I stick square root of 2 in my calculator and press equals, it might come up with a rational number, the square root of 2, the thing which I've just typed. So in order to do that, you should see an S to D button. If you hit that, then it'll bring up a decimal to a number of decimal places. So let's say, for example, this is going to be 1.414, etc., etc., etc. Okay. Now this is actually an irrational number. Reason being is it because it goes on forever and ever and ever, but it never repeats. So 1.414, there'll never be a point where it just suddenly becomes, do you know what, the rest of the digits can all be 9s, or all be 2s, or all be 3s, or whatever. So this is an irrational number. Now actually irrational numbers are really interesting as well. History of maths, there was a guy called Hipparchus that actually proved that the square root of 2 was irrational. Irrational means it's irrational, which means it cannot be written as a ratio or as a fraction. Okay, so these things cannot be written as a fraction. Whereas this is rational. Okay, 1 can be written as a fraction, like 1 over 1, okay, or 2 over 2, or 3 over 3, etc. If I try square root of 3 now, so let's try another integer. Okay, if I stick square root of 3 in a calculator, what does this come out as? Well, it comes out as 1.732, etc., etc., etc. Here we have another irrational number. Okay, so square root of 3 is irrational. Now if I try square root of 4, well, hopefully you realise that's 2. Great, that's rational. Okay, so in other words, squaring any integer will be nice. Okay, we did that right at the very start. This whole act of squaring integers, that will always result in a nice number, okay? But the same is not true of square rooting. So you can't just square root any integer and hope it will come out as a nice number, because sometimes it will be irrational. Okay, so this is where being able to simplify our surds will be nicer. Okay, and it will make things easier to deal with. So we can say then a surd is a square root that results in an irrational number. Okay, so irrational number, remember, is stuff like this. Okay, so this is irrational, this is irrational. It's basically the square root of a number, and it results in a number that looks horrible. It's like got loads of decimal places in, and basically those decimal places will go on forever and ever and ever, and it will never repeat. So it can never be written as a fraction. It's never rational. Okay, so a surd is a square root that results in an irrational number. Now it's okay, we can still work with surds. Okay, oh, by the way, I should just point out, so square root of 2 is a surd, square root of 3 is a surd, but these are not surds. So square root of 1 is not a surd, square root of 4 is not a surd. Reason being is because it results in nice rational numbers on the right hand side. Okay, so a surd must be a square root that results in a rational number. Okay, if it results in a nice integer, it's not a surd. But it's okay. Okay, so even if we have a surd, for example, if I try and find the square root of 12, okay, it's okay. I can still work with this. I can still make this simpler and easier to work with. Okay, and how do I work with it? Well, I basically look at the 12. Okay, I basically look at 12 and I say, can I think of two numbers which multiply together to make 12, but one of those numbers is a square number? Let me say that again, because this is really important. I'm looking for two numbers that multiply together to make 12, but one of the numbers has to be a square number. Okay, what do I mean by a square number? Well, it's quite literally what we're looking up over here. Okay, so these are all square numbers because they're numbers which are a result of numbers being squared. So for example, 16 would be a square number because it's the result of a 4 being squared. Okay, 25 would be a square number because it's the result of 5 being squared. Okay, so let's have a look at square root of 12. So I'm asking myself the question, can I find two numbers that multiply together to give me 12, but one of those numbers is a square number? Well, as an example, let's just try like 2 times 6. That gives me 12, but this is not what I want because I want a square number in there. So 2 is not square and 6 is not square. So let's try another combination. Well, okay, I could write, say, for example, 3 times 4. That would be okay, yeah? Because 3 times 4, 4 is a square number. It's 2 squared, okay? So in other words, I could rewrite square root of 12 as the square root of, instead of writing 12, I'm going to write it as 3 times 4. Or if I prefer, I can rewrite that as the square root of 4 times 3. It doesn't matter what order I write it in, okay? So just by convention from now on, I'm just going to write the square number, in this case the 4, as the first number underneath my square root. Now, the way which this works, and you will be able to prove this later on when you look at indices, the way that this works, I can basically separate this into two square roots. So I can have the square root of 4 and the square root of 3 and still multiply. Okay, so you notice all I've done here is I've separated the 4 and the 3 into two separate square roots. Okay, the reason being is because now I've done that, I can say, square root of 4, that's 2. Because I know that 2 times 2 gives me 4. So in other words, I can write square root of 4 as 2, and I can't really do anything with square root of 3, because if you remember, we did it right at the very beginning, or we did just a minute ago, square root of 3 is irrational, right? So that's still a surd. So in other words, now I can rewrite this, instead of writing 2 times square root of 3, I can just write this as 2 root 3, just like I would with algebra, okay? So in other words, I can say that the square root of 12 can be rewritten as 2 root 3. Now, why do we want to do this? Well, the simple truth is that if we can make the number smaller, you'll be able to approximate it a little bit better. Let me show you a simple example, okay? So square root of 3, if I'm trying to work out roughly what is the square root of 3, well, I know it has to lie in between the square root of 1 and the square root of 4. Now, I wonder if you can think, why have I chosen those two numbers? Reason? They're both square numbers. They're both not surds. So if I ask for the square root of 1, for example, you'd say that's 1. And if I ask for the square root of 4, for example, you'd say that's 2. Okay, so I know that square root of 3 has to lie somewhere along this number line, and it's probably going to lie closer to square root of 4 than it is to the square root of 1. Now just be aware, this is not a linear graph. In other words, the spacing between square root of 1 and square root of 2 is not the same as the square root of, there's a difference between square root of 2 and square root of 3. So it's not the same space. But for small square roots, it's okay. Okay, it's okay to think of them as linearly. So I know it's going to lie somewhere between square root of 1 and square root of 4. Here's square root of 3. And it's probably going to lie closer to the square root of 4 than the square root of 1. So in other words, I know that the square root of 3 is going to lie closer to 2 than it is to 1 as an actual decimal approximation. So I don't know, let's maybe let it equal 1.7-ish. Okay, so if I approximate it, I can say square root of 3 is going to be about 1.7-ish. Okay, which means if I want to find the square root of 12, I know that's going to be 2 multiplied by 1.7-ish. Okay, 1.7-ish. So now if I do 2 times 1.7, that's going to give me 3.4. So in other words, I know then I can approximate that the square root of 12 will be approximately, let's say approximately here. So I use squiggly equals rather than straight equals. So I know that squiggly equals, square root of 12 is going to be squiggly equals 3.4. Stick it on your calculator, see what you get. Okay, so square root of 12, what's that actually going to be equal to? Okay, square root of 12 is actually going to be equal to, hey, that's not bad, 3.5. It's actually equal to 3.46, okay? So 3.46. That's pretty good. So in other words, if you want to approximate decimals, or if you want to approximate surds, as decimals without using a calculator, you can do it by simplifying. Now, let me just give you another example of simplifying surds, because I mean, that was quite an in-depth example. So let's try something like this. Let's try the square root of 8. Sorry, my technology is not working that well today. First my calculator breaks, so I had to drop it, and then my pen is not working great. Okay, so remember, square root of 8. I'm looking for two numbers that multiply to give me 8, but one of those has got to be a square number. You happy 4 and 2 would work? So if I write 8 as 4 times 2, that works because 4 is square. So in other words, I can rewrite this as the square root of 4 times 2. All I'm literally doing is replacing that 8 with 4 times 2. All right, so now I can separate this into two separate square roots. So I can separate this in square root of 4 and square root of 2. Okay, now if I break this down, we'll have a look. Square root of 4 is going to be 2, and square root of 2 I can't really do anything with. So in other words, I can write this as 2 root 2. So square root of 8 simplified is 2 root 2. Let's do another example. Let's take square root of 48. So I want to find two numbers which multiply together to make 48, but one of those has got to be a square number. Now just think, well, 4 works again, so I could write it as 4 times by, what's that going to be? It's going to be, is it 12? Yep. So I could write that as 4 times 12. However, I think there's a bigger square number that goes into 48. I think 16 would work. Okay, so 16 times by 4. I think that would work. Okay, sorry, 16 times by 3, excuse me. I think that would work, okay? And if you wanted to get that, if you couldn't see that directly, then you could actually just have a look at that 12 and say, I can think of a square number multiplied by another number, which gives me 12. We've already done it. So I could write that if I wanted to as 4 multiplied by, and then I break the 12 down into 4 times 3 again. Okay, that's another square number hiding in there. And then I could say, okay, 4 times 4 is 16, times by 3. Okay? So that would also work. So that's the one I'm going to go for. Always try and look for the highest square root if you can. So this will be the square root of, well, 48, I'm going to write that as 16 times 3. Separate that into two separate square roots. That would be square root of 16 times square root of 3. So square root of 16 is 4 times by square root of 3. And then finally, I can just write that as 4 root 3. All right, let's see if we can do one more then. Let's try square root of 75. So again, I'm going to ask myself the question, can you think of two numbers which multiply together to make 75, but one of those numbers has got to be square? Okay, 25 times 3 would work. Okay, 25 times 3. Okay, so therefore I can break this up into square root of 25 times 3, which will break up into square root of 25 times square root of 3, which becomes 5 times square root of 3, because of course square root of 25 is 5, and then this becomes 5 root 3. Okay, so square root of 75 I can break up into 5 root 3. Okay, so this is how you simplify square roots. Now this is really important because, for example, I can give you something like this. Okay, so for example, if I give you square root of 45 plus the square root of 45. Okay, in fact, let's make that square root of 5. Okay, so let's make square root of 45 plus square root of 5. Now at the moment, I can't add these two things together. Okay, just remember with my fractions, if I gave you something like 3/4 plus 4/5, you can't add those two things together because the denominators are different. Okay, it's a bit like saying having 3 quarters plus 4/5. It's a bit like saying 3 dogs plus 4 cats. You can't combine them together. Same thing here. Okay, because you've got different things underneath the square roots, you can't combine them together. But that's okay, because just like we did with fractions, we just had to make the denominators the same. Same kind of principle here. With surds, you have to make the thing underneath the square root the same. So have a look at square root of 45. Let's see if we can simplify this down. Well, have a think. Square root 45. Can you think of two numbers which multiply together to make 45, and one of those things are positive? Well, have a think. I think 9 and 5 would work. Okay, so in other words, I could write square root of 45 as the square root of 9 times 5. Okay, which I could break up into square root of 9 times square root of 5. Square root of 9 is 3, and then I've got the square root of 5. So in other words, I could rewrite this thing, not as a square root of 45 plus root 5, but as 3 root 5 plus root 5. Now I'm in this position, I'm basically saying, well, okay, if I have 3 of something and then I add on another of that thing. Notice that it's root 5. I'm just thinking of it like I do algebra, right? 3 of something plus 1 of something. That's going to give me 4 of something. And in this case, that something is just root 5. So that there would be my final answer. It would be 4 root 5. Let's see it done with another example. Okay, let's see it done with something like this. Okay, let's see it done with 3, let's see it done with 1 plus root 5 times by 4 plus root 5. Let's have a look at this, okay? So this looks a bit more complicated, but do you know how to multiply out two brackets? We've done this in the last video. So let's do this. So 1 times by 4 times by 1 times by root 5. We're just making sure everything in the first bracket meets up with everything in the second bracket. So 1 times 4 is 4, and then 1 times root 5 is positive root 5. Let's do the same with the root 5 in the first bracket. Make sure it meets up with everything in the second bracket. So we have root 5 times 4, that gives me 4 root 5. And root 5 times positive root 5, well, that you could write as root 5 times itself, root 5 squared. Now just have a think. If I take root 5 and I square it, that's basically like saying 5, I square root it, then I square it. Are you happy that those two things just literally undo each other? If I take a number and I square root it, but then I immediately square it again, I'm back to that number, okay? So in other words, I get 4 plus root 5 plus 4 root 5. Oops. That root 5 squared literally just becomes 5. Okay, so take a number, square root it, then immediately square it. That will take me back to 5 again. It's like undoing each other. Square it and the squaring undo each other. Okay, I can also simplify this slightly. Have a look. I have root 5 plus 4 root 5, and I also have the 4 plus the 5. Well, let's do the 4 plus the 5 first. That gives me 9. Then if I have root 5 plus 4 root 5, well, in total, I have 5 root 5s. So that would be my final answer. Okay, let's try this with another example then. Okay, let's try this with this example. 5 root 2 minus 2 multiplied by 3 minus root 6. Okay, 3 minus root 6. So let's have a go at this then. So 5 root 2 multiplied by 3, that's going to give me 15 root 2. Then make sure that 5 root 2 meets up with that negative 6. So be careful, positive times a negative makes a negative. And then 5 root 2 times root 6, well, that's the same as 5. And then just make sure you multiply those two square roots together. So root 2 times root 6 will make root 12. So you can multiply the numbers underneath the square roots. Okay? Then if you do negative 2 times 3 times by negative 2 times by negative root 6. So negative 2 times negative 3, no, times negative 2 times positive 3 makes negative 6. And then negative 2 times negative root 6 makes positive 2 root 6. Okay? Now I can simplify, I can tidy this thing up. Okay? Now, first of all, you're probably looking at this and going, I'm not sure what we can do here. Because if you have a look, there's no way of combining together these square roots at the moment. There's no like terms. So what we need to do instead is actually see if we can simplify anything down. So let's have a look at the root 12, okay? So will the root 12 simplify anything down? Well, yeah, I think we can write that as root 4 times root 3, or we can write that as 2 root 3, okay? So let's have a look. So we've got 15 root 2 minus 5 times by 2 root 3, that makes 10 root 3, minus 6 plus 2 root 6. Okay, so that I think is as simple as we can make it. There's no other square roots or simplifications which we can make. Okay, now one final thing that we want to look at with surds is this idea of rationalizing the denominator. Now we've already looked at this idea of a rational versus an irrational number. Remember, a rational number is the square root of a nice number. Okay, basically it can be written as a nice number, whereas if you take the square root of something like 3 or square root of 2, that results in a horrible number. Okay, so if I give you something like 1 over root 2, basically if I want to rationalize the denominator, I want to take this square root of 2, which at the moment is irrational, and turn it into a rational number. Now, why do we want to do this? Well, if I want to add two fractions together, just remember I need the same denominator. So it's easier to find a common denominator is if we have all nice rational numbers on the denominator. So in other words, I want to get rid of this root 2. So let's take this 1 over root 2 and see if we can rationalize it. Well, we've just seen that if we want to get rid of root 2, if we want to make it a nice rational number, we could, if we wanted to, multiply it by root 2. Okay, if we multiply by root 2, what do we get on the denominator? So just focus on the denominator first. Well, root 2 times root 2, that's root 2 squared. Well, the square root and the square, they cancel each other out, means we're just going to be left with 2. Okay, but of course, we can't just multiply by root 2 on the denominator. We've also got to multiply by root 2 on the numerator. Now just pause for a second. Why is this okay? Why is multiplying by root 2 over root 2 okay? Well, the reason is because we're effectively just multiplying by 1. Okay, we've not changed the value of this fraction. Remember, if you've got the same numerator and denominator, you're just multiplying by 1. Okay, so on the numerator, if I get 1 times root 2, I get root 2. On the denominator, I've got root 2 times root 2, that's 2. Just check, is that denominator rational? Yes, it is. Okay, so let's try with another example. Let's try like 6 over root 6. Okay, so let's just follow the same principle as before. We multiply by root 6 over root 6. That's the same as multiplying by 1. So we get 6 times root 6 on the numerator. That's 6 root 6. And on the denominator, we get root 6 times root 6. Well, that's root 6 squared, which remember is just 6. Okay, and you notice I can make a simplification here. I can cancel off my 6's. So in other words, I'm just left with root 6 here. Root 6 over 1 or just root 6. All right, let's try with another example. Let's try something like 1 over 4 root 5. Now have a think. You could, if you wanted to, multiply by 4 root 5 over 4 root 5. However, in this case, there is not really much need to, okay? Because just think, the only thing that's making that denominator irrational at the moment is the root 5. So if I multiply by root 5, then I'm going to get root 5 times root 5, which is 5, then just become 4 times 5. That's rational anyway. Okay, so actually, I could just get away with multiplying by root 5 over root 5. If you wanted to multiply by 4 root 5 over 4 root 5, fine, but it's just going to make your life more difficult. Just get away with multiplying by root 5 over root 5. That's the thing that is making the denominator irrational. So on the numerator, I get root 5. On the denominator, I get 4 root 5 times root 5. Well, that's the same as 4 times 5. We've already just seen that, which means that I get root 5 over 20 here, and that works, okay? Let's try with one final example then. Let's try with 4 plus root 2 over 3 root 2, okay? So again, what am I going to multiply by? Well, look at the denominator. What's making that thing irrational? I need to multiply by root 2 over root 2. Okay, now let's have a go at this. I'm going to write it out longhand. If you're okay with multiplying out brackets in your head, fine, but I'm going to multiply it longhand just to make sure we're okay. So we're going to get root 2 multiplied by 4 plus root 2. All divided by, we'll have a look on the denominator. I get 3 root 2 times by root 2. That's the same as 3 times 2. Now if I multiply out that numerator, I get root 2 times 4, which is 4 root 2. I get root 2 times positive root 2, which is 2. So you notice all I've done there is just literally multiplied that root 2 out, distributed it across the bracket. And the denominator, I get 3 times 2, which is 6. Now I am going to take this one step further to properly simplify it. If I separate these two things out, so they're both over 6, like so. So all I've literally done here is almost drawn an imaginary line down the middle and then just separate it out so it's both over 6. Okay? So therefore, what I can do is I can say, have a look here. I've got 4 and I've got 6. That will cancel. I can divide top and bottom by 2. That will cancel to 2 over 3. Okay? Same thing there. I can divide top and bottom by 2, which give me 1 over 3. So in other words, this final thing could simplify to 2 root 2 over 3 plus a third, which I can finally put back together as 2 root 2 plus 1 over 3. So that would be it fully simplified. Okay. Now, one final thing, let's have a look at rationalizing the denominators with slightly more complicated examples. So this was question 5. Let's have a look at a slightly more tricky example. Let's have a go at, for example, 1 over 1 minus root 7. Now, what I'm going to do here is multiply by 1 plus root 7. So I could try multiplying by root 7, but I wouldn't get very far because I still have an irrational thing on denominator, because when I multiply by root 7 here, sure, this thing will be rational, but this thing won't be. Okay, and try that yourself if you're not convinced. But just for the sake of time, I'm just going to show you what you need to multiply by. I'm going to use this idea of difference of two squares. Okay, so if you're familiar with difference of two squares, it's basically 1 plus something multiplied by 1 minus something, and effectively you should end up with the difference of two squared. So 1 squared, so a squared minus b squared. Okay, if of course those two numbers are squared to start off with. So let me show you what I mean here. Okay, what I'm going to multiply by is not 1 minus root 7, I'm going to multiply by the conjugate. So the conjugate means still keep the 1, still keep the root 7, but I'm going to change this minus to a plus. Okay, so this then would become 1 plus root 7 on the numerator as well. Now if you're looking at that and going, what on earth are you doing? Trust me, just follow it out and I'll show you why this works. Okay, so if I multiply on the numerator, 1 times by 1 plus root 7, well 1 times anything is just itself. So on the numerator I get 1 plus root 7. Then the denominator, we'll have a look. Let's write it out longhand first of all. 1 minus root 7 times by 1 plus root 7. Let's have a look at that. Okay, so if we expand that out, what do we get? Well, we've still got 1 plus root 7 on the numerator, but on the denominator, let's just do it. Let's see if we can do it in our heads. So we need to make sure the 1 multiplies with everything in the second bracket. So 1 times 1 is 1. 1 times positive root 7 is positive root 7. Now let's move on to the negative root 7 and multiply with everything in the second bracket. So negative root 7 times 1 is negative root 7. And negative root 7 times positive root 7, well, that'd be negative 7. Okay, now watch what happens. Do you see that I've got positive root 7 and negative root 7 there? They cancel, okay? Which means that I will just be left with 1 plus root 7 on the numerator. Now on the denominator, I end up with 1 minus 7, which will be negative 6. Okay, negative 6. Now this will always be true. Okay, so if you're looking at this and going, why are you multiplying by the conjugate? If you multiply something by the conjugate, it means that you will always end up with a nice rational number in this case. Okay, so just change that negative to a plus or that plus to a minus and you will be golden. Okay, now let's just show you this works with a slightly more complicated example. Let's try 8 over root 5 minus 6. Okay, let's see what we get here. So first of all, let's multiply by the conjugate. Well, all I need to do is keep the root 5 the same, the 6 the same, but I'm going to change the minus to a plus. Okay, so I get root 5 plus 6. Now let's see what happens. Well, okay, on the numerator, I get 8 times by root 5 plus 6. All divided by, on the denominator, I get root 5 minus 6 times by root 5 plus 6. Okay, let's see what we get. Well, 8 times root, let's do the numerator first. So 8 times root 5 is 8 root 5. 8 times positive 6 is positive, what's that, 48. Then denominator, well, root 5 times root 5 is 5. Then I get positive 6 root 5, but then I'll also get negative 6 root 5 when I multiply these two things together. So I'm not actually going to bother writing that. So it's just going to be negative 6 times positive 6, which is negative 36. If you wanted to sit down and actually formally write it out, just to convince yourself that those 6 root 5s would cancel, that's fine, but I'm just going to leave it like that. Okay. Then finally, I get 8 root 5 plus 48 divided by, well, 5 take away root 6 is, so 5 take away 36 is negative 31. So I could leave it like this if I wanted to. Okay. Now I will just show you that I could simplify this even further. Okay. If you have a look at this numerator, okay, this is all positive. On denominator, I've got negatives. I could actually make this look slightly better. Okay. If I have a look at that numerator, if I preferred, I could treat this as dividing everything by negative 31. So if I divide everything by negative, okay, so if I divide this by negative and this by negative, then what I will end up with is negative 8 root 5, but then I'd end up with negative 48. And denominator, I'll end up with 31. So that is also fine to leave it like that if I wanted to. Then if I wanted to, I could factor out my negative and just end up with 8 root 5 plus 48. So there's 3 forms which you could leave your final answer in. So that's all negative. So any of these 3 forms is totally fine. Okay, let's just look at one final example, then I'll set you your homework. So we're not going to have time to look at indices today. We'll look at those in the next video. Okay, so let's have a go at something like root 2 over root 8 plus root 12. Now, as you get more experience with this, as you get more experience with surds, you may start to notice, I can actually simplify these things down. So for example, because I've done loads of these, I recognise that root 8 and root 12 can both be simplified. So let's start off by doing that. Make our numbers smaller before we go. So okay, let's try this. Root 8, how could I rewrite that? Well, I could rewrite that as root 4 times root 2. That would work, wouldn't it? Then that would just be 2 root 2. Let's try root 12. Well, okay, I could rewrite that as root 4 times root 3. So that would become 2 root 3. So actually, I'm just going to rewrite this as root 2 over 2 root 2 plus 2 root 3. So you can see all I've literally done here is I've just changed the denominator and I've simplified it before I start. Now I can rationalise my denominator. So just remember, to rationalise the denominator, I change this to a minus. So I end up with 2 root 2 and 2 root 3, same as before, but I change my plus to a minus, like so. And same on the numerator, like that, okay? So now if I multiply all this out, I get root 2, so don't do the multiplication in your head, write it out, I get root 2 multiplied by the entirety of the thing on the numerator of the second fraction. So I get root 2 multiplied by all of this, okay? Then denominator, again, I get 2 root 2 plus 2 root 3 multiplied by its conjugate. So 2 root 2 minus 2 root 3. Now, if you've not had much practice with this, it might take a little bit of time to expand this out, but hopefully you realise it's just difference of 2 squares, okay? So in other words, let me start off with the denominator first. It will be this thing times this thing, okay? So 2 times 2 is 4, root 2 times root 2 is 2, okay? The middle 2 terms are going to cancel, which means I just need to multiply these 2 things together and there'll be a minus in the middle. So I get 2 times 2, that's 4. Root 3 times root 3, that's 3. Okay, there's a minus in the middle. Now if I focus on the numerator, we'll just remember I need to multiply root 2 by everything on the numerator. So let's have a look. Root 2 times 2 root 2, let's do the first one. So I get 2 times by root 2 squared, which is 2 times 2, that gives me 4. Then I get root 2 times by negative 2 times root 3. Well, that gives me 2. Well, root 3 times root 2, that's root 6. All right. So again, more practice you do, you'll be as quick as me. Okay. Now just finally simplify this down. Well, I get 4 minus 2 root 6. Then denominator, I get 4 times 2, which is 8, minus 4 times 3, which is 12. Let's have a look what I've got here. All right, so I got 4 minus 2 root 6. On denominator, I get negative 4. Okay, I get negative 4. Now, I can actually simplify this even further. Let's first of all deal with the negative. Okay, so I'm going to divide this by negative and this by negative. Okay, well, if I divide positive 4 by a negative, that will become a negative 4. Okay, that will become a negative 4. And if I take negative 2 and divide it by a negative, sorry, negative 2 root 6 and divide by a negative, that will become a positive 2 root 6. On denominator, I've still got 4. Okay? And then finally, I can just say, what I can do here is divide that by 4 and divide that by 4. Okay, so let's see what I get. Let's separate it out. So I get negative 4 over 4 plus 2 root 6 over 4. Okay, let's break this down. So negative 4 over 4 is negative 1. And then positive 2 root 6 over 4 is positive root 6 over 2. Okay, so just because I prefer starting off on a positive, I'm just going to switch these two terms around. We're going to do a quick switcheroony. All right, so I'm going to have root 6 over 2 minus 1. And I would leave my final answer like that. Okay, so hopefully that makes sense with surds. Like I say, we've not had much time to finish off indices, but we'll do that in the next video. So can I ask you then, for the weekly task, to have a go at this question here? And again, bring this along to your lesson, your next lesson. Okay, so we're going to do 3 plus root 3, all divided by 6 root 48 minus root 75. Can you simplify this? Okay, notice I'm using the word simplify again. Here, what do I mean by simplify? Simply rationalize the denominator. Okay, make this a lot simpler. So there's fewer square roots going on, there's fewer surds. So can I give you that as a weekly task, and please bring it along to the next class? Okay.